In this module, you will learn to identify and combine mathematical statements. Let's look at some sentences. Mumbai is the capital of Maharashtra. 2 is an odd number. He is a good batsman. Can you say the truth value of these sentences? We know that Mumbai is the capital of Maharashtra, and thus this sentence is true. The second sentence, 2 is an odd number, is false. Let's consider the third sentence. Here, the information is not sufficient to say whether this sentence is true or false. Here the word he is uncertain. Even if we know the batsman, it is not sufficient to decide whether he is a good batsman. This again depends on the perception of a person. It means that the given sentence is ambiguous. The first two sentences have truth values and there is no ambiguity. Mathematically, such sentences are called statements. A sentence is called a mathematically acceptable statement if it is either true or false. Let's look at more sentences and justify their truth values. In these sentences, the first two sentences are true, while the third and fourth sentences are false. In the last sentence, it is not certain to say how far Hyderabad is from another place, unless it is mentioned. Therefore, the first four sentences are statements. Hyderabad's distance is different from different places. Thus, this sentence is not a statement. Usually, mathematical statements are denoted by lowercase letters like P, Q, R, S, and so on. The statements that you saw here are very short and cannot be broken into smaller statements. These are called simple statements. Let's consider the statements given. Statement P is 2 is an even number. Statement Q is 2 is not an even number. Do you notice any relation between the two statements? Statement P is true, while statement Q is the denying statement P. This implies that statement Q is false. Such a statement is called the negation of a statement. The denial of a statement is called the negation of the statement. If P is a statement, then the negation of P is also a statement, and is denoted by a tilde symbol followed by the statement name. This is read as not P. If the truth value of P is true, then the truth value of not P is false, and vice versa. Next, we'll frame some negations of given statements. Remember, we commonly use phrases like, "It is not the case," or "It is false that," while forming the negation of a statement. The negation of P is either, "It is not the case that 5 is an odd number," or "It is false that 5 is an odd number." In other words, it can be written as 5 is not an odd number. Many a times, we come across simple statements that we need to combine into a single statement. Such statements are called compound statements. A mathematical statement obtained by combining one or more simple statements using some connecting words like and, or, etc. is called a compound statement. Generally, we use the words and, or, and so on to connect simple statements. Let's consider the statement 5 is both an odd and a prime number. This statement tells us that 5 is an odd number and 5 is a prime number, and that they are connected with the word and. The simple statements that form the compound statement are called component statements. Let's combine the given statements using the word or. The compound statement obtained is x is either a rational number or an irrational number. In this module, you will learn to justify the truth value of a compound statement and identify quantifiers in mathematical statements. We know that a compound statement is a combination of two or more simple statements using words like and, or, and so on. Such words are called connecting words. Let's consider the statement 24 is divisible by 2 and 4. Can you say the truth value of the given statement? In order to determine the truth value of the compound statement, we first need to find its component statements. The component statements of the given statement are 24 is divisible by 2. 24 is divisible by 4. The connective word is and. A compound statement with the connective word and is called a conjunction. The truth value of a conjunction statement depends on the truth values of its component statements. The truth value of the conjunction is true if the truth values of all the component statements are true. The conjunction is false if any one of the component statements is false. Let's consider the component statements of the given compound statement again. We know that both the statements are true. Therefore, the compound statement is also true. Let's consider another compound statement. 9 is an odd number and a prime number. The component statements of the compound statement are 9 is an odd number. 9 is a prime number. Statement P is true, while statement Q is false. Therefore, the compound statement is false. Please remember that every statement with the word and cannot be considered a conjunction. For example, Jammu and Kashmir is a state of India. In this statement, the word and is used to combine two words and not two statements. Therefore, the given sentence is a statement but not a conjunction. Let's look at the given compound statements. In both the sentences, the connective word used is or. A compound statement with a connective or is called a disjunction. Let's determine the truth values of the given statements. Here are the rules that we will use to determine the truth value of compound statements with the connecting word or. A compound statement with or is true when at least one component statement is true. A compound statement with or is false when all its component statements are false. Let's begin with the first statement. 24 is a multiple of 2 or 4. First, break the compound statement into its component statements. Here both the component statements are true. Therefore, the compound statement is also true. Next, the component statements of the compound statement, a triangle has 3 sides or 4 sides, are: a triangle has 3 sides, a triangle has 4 sides, statement P is true, while statement Q is false. Therefore, the compound statement is true. Let's look at another example. Plants do not take carbon dioxide or do not give oxygen. The component statements of the given statement are: plants do not take carbon dioxide. Plants do not give oxygen. We know that both the statements are false. Therefore, the compound statement is also false. The connective OR in a compound statement can be either exclusive or inclusive. Let's first consider the statement, Ramesh will go to Delhi by flight or by train. In this case, Ramesh cannot go to Delhi by both flight and train. He can go by either mode. If he travels by one, he cannot travel by the other at a given time. In such sentences, OR is exclusive. In the next statement, Rohit should have a voter card or a passport for identity proof. He may have both, and having one does not exclude the possibility of him having the other. Here, OR is inclusive. We have seen compound statements with the connective words AND, OR. In mathematics, we come across statements that contain phrases like for all, for every, for some, there exists. These phrases convey the idea of quantity and refer to a specific collection of objects. Such phrases are called quantifiers. Quantifiers such as for all, for every, and for no are called universal quantifiers because they make an assertion about every member of the universal set under consideration. The universal quantifier is denoted by the symbol shown. The quantifiers there exists and for some are called existential quantifiers. The existential quantifier is denoted by the symbol shown. In this module, you will learn to determine the truth value of implication or conditional statements. We know that a compound statement is the combination of two or more simple statements using AND, OR, and so on. Let's consider another type of compound statement. If you work hard, then you will pass the examination. This statement involves two statements. You work hard, you will pass the examination. Now, the compound statement can be expressed as if P, then Q. In this case, if statement P is true, then statement Q will be true. Such compound statements are called implications or conditional statements. It is formed using the connecting words if-then. The implication can also be written as P implies Q. This is represented using the arrow-like symbol as shown. The symbol stands for implies. Note that a compound statement, if P then Q, is always true, except in the case when P is true and Q is false. because a true statement cannot imply a false statement. That means, if you do not work hard, then you cannot say whether you will fail or pass the examination. In other words, P not happening has no effect on whether Q happens or not. Let's consider another statement. If 3 is a factor of 9, then it is also a factor of 18. The component statements that are involved in it are 3 is a factor of 9, 3 is a factor of 18. Statement P implies statement Q, or 3 is a factor of 9 implies that 3 is also a factor of 18. The implication or conditional statement P implies Q can also be expressed as shown. Let's look at the converse, inverse, and contrapositive of an implication. Consider an implication P implies Q. The converse of the given implication is Q implies P. The inverse of the given implication is given by negation P implies negation Q. The contrapositive of the given implication is negation Q implies negation P. Let's write the converse, inverse, and contrapositive of the implication. If two sides of a triangle are equal, then it is an isosceles triangle. The component statements of the compound statement are: two sides of a triangle are equal, the triangle is isosceles. The implication of the statements is P implies Q. The implication or conditional is: if two sides of a triangle are equal, then it is an isosceles triangle. The converse of the implication is: if a triangle is isosceles, then two of its sides are equal. The inverse of the implication is: if two sides of a triangle are not equal, then it is not an isosceles triangle. The contrapositive of the implication is: if the triangle is not isosceles, then two of its sides are not equal. Let's look at another implication. If the sides of a triangle are equal, then its angles are also equal. The converse of this implication is: if the angles of a triangle are equal, then its sides are also equal. Here both the statements are true. Such statements can also be expressed as: the sides of a triangle are equal if and only if its angles are equal. Such compound statements are called a by-implication or by-conditional. A compound statement involving statements P and Q, which is in the form of P if and only if Q, is called a by-implication or by-conditional. A by-implication is represented by a double imply symbol. The by-implication P if and only if Q can also be expressed as shown. Remember here that if P and Q have the same truth values, either true or false, then the by-implication is true. If either P or Q is false, then the by-implication is false. In this module, you will learn about different methods used to validate mathematical statements. We know that every mathematical statement is either true or false. We know that the truth value of a compound statement depends on the truth values of the component statements involved in it. How can we verify if the truth value of a component statement is correct? The answer to this question depends on the connective words, quantifiers, and implications involved in the compound statement. To validate such statements, we follow certain rules. Let's discuss the first rule. The first rule is used to validate compound statements with the connective word and or conjunctions. To validate whether a conjunction is true, we have to show that all of its component statements are true. P and Q are mathematical statements. To show that the statement P and Q is true, we need to show that both the statements are true. Let's check the validity of the statement. 2 is a positive number and a prime number. The component statements of the compound statement are: 2 is a positive number, 2 is a prime number. We know that component statements P and Q are true. Hence, it is validated that the given compound statement is true. Rule 2 is used to validate compound statements with the connective word OR. To validate whether a disjunction is true, we have to show that one of its component statements is true. If P and Q are mathematical statements, then in order to show that the statement P or Q is true, we need to show that either statement P is true or statement Q is true. Let's check the validity of the statement. 5 is a factor of 21 or 30. The component statements of the compound statement are: 5 is a factor of 21. 5 is a factor of 30. We know that statement P is false, while statement Q is true. Hence, it is validated that the given compound statement is true. Rule 3 is used to validate statements with if-then or implications. To prove the statement if P then Q, we need to show any one of the cases shown is true. By assuming that P is true, show that Q must be true. This is called the direct method. By assuming that Q is false, show that P must be false. This is called the contrapositive method. Let's prove the statement. If x is odd, then x squared is odd. The component statements of the compound statement are: x is odd, x squared is odd. To validate the given compound statement, let's consider that the statement P is true. Let x be 2n plus 1 for some integer n, by the definition of odd number. Therefore, x squared is equal to 2n plus 1 whole squared. On simplification, we get 2 multiplied by 2n squared plus 2n plus 1. This is also an odd number. This shows that x squared is also odd. Hence, the given statement is proved. Rule 4 is used to prove by implications. To prove the statement P if and only if Q, we need to show that if P is true, then Q is true. If Q is true, then P is true. Let's prove the statement. X minus 2 is negative if and only if x is less than 2. This statement can also be broken down as: if x minus 2 is negative, then x is less than 2. If x is less than 2, then x minus 2 is negative. Here both the implications are true. Therefore, the by implication is true. Hence, the given statement is proved. However, we come across some mathematical statements that cannot be proved directly. such statement. However, we come across some mathematical statements that cannot be proved directly. Such statements can be proved by the contradiction method. In the contradiction method, to prove a statement P is true, we first assume that P is not true, or negation P is true. Then, we arrive at some result that contradicts the assumption. This concludes that P is true. We cannot prove that a statement is false by the methods that we have discussed earlier. In such cases, the counterexample method is used to prove a statement. In this method, we take the example of a situation where the statement is not valid. Such examples are called counterexamples. 3 plus x multiplied by 3 minus x is not equal to 9 plus x squared for all integer x. This can be proved by taking a counterexample. Now, consider x equal to 0. Let's substitute the value of x in the given statement. On simplification, we see that 9 is not equal to 9, which is a contradiction. Hence, the given statement is false.